Hello, welcome back to Learn Physics. In today's topic, we are continuing with our current electricity chapter. So yesterday we learned about the mobility and Ohm's law, and I gave you some questions also to check the concept. Okay. So first one, why do the free electrons in a metal wire flowing by themselves not cause any current flow in the wire? Okay, so free electrons are there in the conductor. Then why these free electrons are not causing a current in the conductor? Because we know in conductor the average velocity of the free electrons are equal to 0. Electrons are moving from one point to another point, but the average velocity of the electrons, while we are considering, it is equal to 0. That is why these metals won't be giving this current. Okay, so the next one is, how does the drift velocity of the electrons in a metal conductor vary with increase in temperature? Drift velocity, how does the drift velocity varies with increase in temperature? Vd equals minus EE by m into 2. So as temperature increases, what will happen? Relaxation time decreases. If relaxation time decreases, what will happen? Where drift velocity also decreases. Okay, so as temperature increases, drift velocity decreases. Okay, so next is, two different wires X and Y of same diameter but different materials are joined in series across the battery. If the number density of electrons in X is twice that in Y, find the ratio of drift velocities in the two cases. Okay, number density of X and Y are having same diameter but different materials. The number density of electrons in X is twice that in Y. Okay, so n of X is equal to 2 into n of Y. Find the ratio of drift velocities in these two and electrons in these two wires. Okay, Vd equals minus EE by m into 2. Okay, so we drift velocity, this equation is not sufficient. So here n, including n, which formula we know? I is equal to n a Vd into E. So n also is there in the equation, drift velocity also there in the equation. So we can write it as Vd equals I by n a E. Right. Now for X and Y. For X and Y. For X, while we are considering drift velocity, Vd equals I by nx a into E. A is same because radius is same, they are telling. So it's same. Now Vd of Y, that is equal to I by ny ae. Nx is 2 ny ae. Here it is I is equal to ny by e. So Vd of X and this is Vd of Y. Vd of X divided by Vd of Y, that is equal to I by 2 ny ae into ny ae divided by I. So I and I will get cancelled, ny ae will get cancelled. So this is equal to 1 by 2. Okay, so this is the ratio. That means Vd y will be equal to twice that of Vd x. Okay, here Vd nx is equal to twice ny. So the final answer Vd y equals 2 times 2 Vd of x. Drift velocity of wires equal to twice the drift velocity. As the number density increases, what will happen? Drift velocity decreases. As the number density increases, drift velocity decreases. Clear? So now yesterday we learned about this Ohm's law, and V is equal to IR, and from I is equal to NA VDE, while we are substituting we got the equation for R as ml by a Na square 2. From there we learned as for a particular material R is proportional to L by A. For changing this proportionality sign, we are multiplying it with the constant rho into L by A. Okay, so rho is called as resistivity of the material. Resistivity of the material or specific resistance, or it is called as specific resistance. Okay, so rho is resistivity or specific resistance. So comparing these two equations, can you tell what is the value of rho? Rho will be equal to m by Ne square 2. As we said yesterday, so here specific resistance or resistivity, depending on which and all factors, it is depending on m, it is depending on n, depending on E, charge of electron, that is constant, so it is not, we can't, no need to say about this one, and it is depending on the relaxation time also. Okay, rho equals m by Na square 2. So it is depending on the number density of electrons, that is inversely proportional. Okay, rho is inversely proportional to number density. It is depending on the number density, means rho is having first dependence with number density. That means it is depending on the material. Okay, as material changes, number density also will be number of free electrons will be changing over there, right? So it is depending on the material. Next, rho is inversely proportional to relaxation time. It is relaxation time means it is the time gap between the two successive collisions. Okay, that is relaxation time. That means as temperature increases, what will happen? Tau will be decreasing. Okay, time between two successive collision decreases. So what will happen to rho? Rho will be increasing. So as temperature increases, rho will increase. Okay, specific resistivity or resistivity will be increasing. Okay, so rho is a term which is depending on the material to material, it will be changing. As temperature increases also, rho will be changing. Okay, so clear about this. What will be the unit of this resistivity? Resistivity, for this resistivity, if I am writing one equation, it will be Ra divided by L. R is ohm, right? A is meter square divided by meter. So we will be getting it as ohm meter. That is the unit of resistance. Okay, resistivity. Unit of resistivity is ohm meter. What will be the dimension? Dimension of rho. How we can write down the dimension? Yesterday we had given the dimension of R. Remembering? So V is equal to IR. So R will be equal to dimension of R. I'll write down over here. Dimension of R equals dimension of V divided by dimension of I. V is the potential difference. Work done divided by charge. Okay, work done divided by charges, work done divided by charge. Okay, charge we can write it as Q equals I into T. Okay, work done will be equal to energy, so it will be equal to ml square T to the power minus 2. So it will be ml square T to the power minus 3 A to the power minus 1. This T also will be going upward, ml square T to the power minus 3 A to the power minus 1. So here we can write it as ml square T to the power minus 3 A to the power minus 1 into L square divided by L. So this will be getting cancelled. The final answer will be m L cube T to the power minus 3 A to the power minus 1. This is how we will be finding out the dimension of this resistivity. Okay, so this and all we learned yesterday. Okay, I explained. That is why I didn't tell anything in detail about this resistance. So clear what is meant by resistivity? So resistivity is a term which is depending on the material. Depending on material, that is material to material it will be changing. It is not depending on, we are not telling any dependence with the length or area of cross section. But resistance was depending on length and area of cross section. But here this is changing from material to material and depends on temperature also. Clear? So next we are going to study about the current density. What is meant by current density? Current density is the amount of current flowing per unit area through the conductor. Okay, amount of current flowing per unit area, that is I by A. Its representation is J. Okay, J will be equal to I by A. Okay, we know it is always area will be acting perpendicular to the, it will be acting normal to the surface, right? So it will be always acting normal to the surface. And current density, whether it is a vector quantity or it is a scalar quantity, current density is a vector quantity. Okay, it's a vector quantity. Okay, A will be, see here if I am considering the surface like this, area will be acting perpendicular to it. Instead of that, if I am considering the area like this, area will be perpendicular to this. That means perpendicular to, normal to the surface. Area vector will be acting normal to the surface. Now I will be acting in this manner. So we should consider the components. This is the area component which is making an angle theta with the I. Then what will be the area component which is acting along the current? A cos theta. Okay, so here we can write it as I is equal to J into A cos theta, or we can write I is equal to J dot A. Clear? So I is acting, I and J are area vector are acting on the same line. Okay, say it should be parallel to each other. So then if I is acting in this manner and it is I, this is the, so if this is the surface, if this is the conductor and I is acting in this manner, area is acting in this manner, we should consider the component of A which is acting through this current acting through the conductor. Okay, so it is equal to J dot A. So J and A are vector quantities, dot product is a scalar quantity. So as we said earlier classes, I is a scalar quantity. Okay, I is equal to J dot A. Now we got the value of J in terms of J. Now what will be the unit of current density? Unit will be ampere per meter square. Unit of current density is ampere per meter square. So here we know, see I equals NaVdE. Here I equals NaVd into E. Then what will be this I by A? NVd into E. Okay, what is I by A? J. J equals NVd into E. That is, I can represent Vd as EE by M into 2. So capitally E square by M into 2. That is J value in terms of N electric field 2, in that value we can represent like this. Okay, this is about the current density. Now another term is conductivity. What is meant by this conductivity? Conductivity is how much current can be, see what is the amount of conductance, that is if current can flow easily through the conductor, so what will be that amount? It can be represented as conductivity. Okay, here we learned about the resistance and resistivity. So that is stopping the, or it's a hindrance for the movement of current, right? So it, which is allowing the current to flow through the conductor, that is conductance and conductivity. So next we are going to study about the conductance and conductivity. Next is about the conductance and conductivity. Conductivity. Okay, just opposite to resistance is conductance, just opposite to resistance is resistivity is conductivity, okay, which is helping, which how much easily the current can flow through this conductor, that is called a conductance. Okay, so conductance opposite to resistance I told. So it is represented as 1 by R G equal. G is the representation for conductance. Okay, G equals 1 by R. So we know V equals IR. So V by I equals R. Then what will be this one? This will be equal to I by V. What will be the unit? Ohm inverse. That will be the unit of conductance. Okay, or in terms of M, N and all, if we are writing G, we can write it as A N E square tau divided by M L. Okay, and this, what about the conductivity? Conductivity, I told it is the reciprocal of resistivity. So sigma is the representation of conductivity. It is represented as 1 by rho. Rho is the resistivity. Sigma is the conductivity. So we can write it as N E square tau divided by M. Okay, resistivity is opposite, this reciprocal of resistivity is called a conductivity. Then tell me what will be the unit of conductivity. Conductivity, resistivity is ohm meter, right? So ohm inverse, meter inverse. Okay, this will be the unit of conductivity. So what about the temperature dependence? As temperature increases, tau, what will happen? Tau will decreases and conductivity also will be decreasing. As temperature increases, conductivity decreases. Okay, now we can represent, how we can represent in terms of sigma and all, J's and sigma and all, how we can represent Ohm's law. Microscopic form of representation of Ohm's law. Okay, we know that I is equal to NAVDE. Okay, I by A equals NVDE. Okay, then this VED we can represent it as EE by M into 2 into E. So N is square E by M into 2. What is this N E square tau by M? So what is this value? Tell me. N E square tau by M. That is sigma. Okay. So what is I by A? I by A equals J. J equals sigma into E. This is another form of representation of Ohm's law. Okay, this is J equals sigma E is the microscopic form of representation of Ohm's law. Clear? So this is very important. As temperature increases, conductivity decreases, and as temperature increases, resistivity increases. Okay, and if resistivity increases, resistance also increases, right? So not only see how resistance will be varying according to temperature. See, R is equal to R0 into 1 plus alpha T plus beta T square. This is the representation. This is how the resistance will be increasing in this way. Okay, since the temperature difference is very small amount, usually we won't consider this T square term. So R will be equal to, R at temperature T will be equal to R0 into 1 plus alpha T. This is how the resistance, as temperature increases, resistance will be increasing in this manner. Okay, and one more thing here, how the sigma and this relaxation time as temperature and sigma, how it is depending means it is inversely proportional. So if they are telling you to draw one graph relating this conductivity and temperature, how you will draw? It will be an inverse dependence. So this is sigma and this is temperature. As temperature increases, sigma is decreasing. Okay, this is how the graph will be. Clear? So we will do some numerical relating to this. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 2.5 into 10 to the power minus 7 meters square, carrying a current of 2.7 ampere. Assume the density of conduction electrons to be 9 into 10 to the power 28 meter to the power minus 3. So we should find out the average drift speed. estimate the average drift speed we should find out. In a cross sectional area, A equals 2.5 into 10 to the power minus 7 meter square, carrying a current of I equals 2.7 ampere. Assume the current density of conduction electrons to be, that is N. N is equal to 9 into 10 to the power 28 meter. Number density means number of electrons per unit volume, right? That is why meter to the power minus 1. Tell me how we can find out I is equal to NAVDE. It's a direct question. So we can find out VD as I by NA into E. So what is I here? I is equal to 2.7 divided by 9 into 10 to the power 28 into 2.5 into 10 to the power minus 7 into 1.6 into 10 to the power minus 19. Okay, while solving you will get the final answer. Clear? So the next one is a conductor of length L connected to a DC source of EMF E. The drift velocity of the electron is Vd. If the length of the conductor is tripled by stretching it, by keeping E as constant, find its drift velocity. So here first we need to find out what and all are given. L is the length and E is the EMF. Okay, and Vd is the drift velocity. If the length is tripled, what will happen to the drift velocity? That is the question. So we know the relation connecting Vd equals EE by M into 2. But here it is not having any dependence with the L. So we are trying another equation. I is equal to NAVD into E. Okay, this NAVDE. This equation I am considering. I is equal to E by R. Okay, that is equal to NAVD into E. R equals rho into L by A. So substituting that one, E by rho L into A, that is equal to NAVDE. A and A will get cancelled. Okay, so we are getting Vd is equal to E divided by rho L N E. Clear? So we are getting Vd as E. So Vd is inversely proportional to L. So if it is tripled, length is tripling, what will happen? It is 1 by third. So Vd dash will be proportional to 1 by 3L. So what is Vd divided by Vd dash? Vd divided by V dash equals 1 by L divided by 1 by 3L. So we are getting Vd dash equals Vd divided by 3. Okay, clear? This is so if we don't have any direct relation, by applying two or three equations we can find out some relation among themselves. Okay, so clear? Okay, I am winding up for today. In next video I will be coming with the next portion. If you like the channel, please don't forget to subscribe, like and share. Thank you for watching. Bye.